Welcome to Innovate and React. I'm your host, Kevin Hares, and this episode will be about sustainable chemistry and how we can replace critical materials like platinum group elements in the synthesis, which are crucial catalysts for many important reactions in the chemical industry. And today I'm with Soumyadeep Chakrabortty. He is currently at the Max-Planck-Institute for Kohlenforschung. Welcome, Soumyadeep.
Hi, Kevin. Thank you very much for the invitation. It's nice to see you, and I'm very much looking forward for today's discussion.
Great. Yes, nice to connect again. We met at the LICAT in Rostock, where you also did catalysis research. And maybe for this discussion, let's start with the sustainable chemistry. Like, why do we need sustainable chemistry?
Let's keep it a bit more general for the sake of the audience. So, as you probably know, like sustainable or chemistry in general is really connected to our daily life, as well as starting from metals and synthesis for pharma. And nowadays, let's say in last 20 years or more than 20 years or so, there's an increasing concern about sustainability in chemistry. Sustainability in chemistry in general is a broad term, right? So it's pretty hard to, let's say, define or circle it. Even if you improve a certain reaction, let's say from 100 degrees centigrade to 60 degrees centigrade or 50 degrees centigrade, that's even more sustainable.
Yeah, I think the goal always is to go from like the past, where this cliche of the always polluting chemical industry, where it's like they are just putting out all these toxic gases and toxic wastewater, and they are just producing for the sake of their own money. But especially in the chemical research and in the recent years, this sustainable chemistry movement has been really a motivation for a lot of scientists to improve reactions, make them more efficient in terms of energy, but also in terms of resource use, high selectivities, which in the end always also means that you can make more money because in this way it's aligned, because if you have your reaction and you get high percentage of what you actually want and you don't have a lot of waste, it's positive for the environment, but it's also good for the company, right?
Yeah, I totally agree with you. So even nowadays, a lot of companies even are focusing on sustainable chemistry, and they're slowly trying to change their setup or their methods for making chemicals, but in a more sustainable way. Let's say a pharma or a small molecule pharma, which was made 20 years back, let's say using a palladium, which is considered as a precious metal catalyst. So in terms of price, in terms of toxicity and so on. So people are now more focusing on trying to replacing, let's say, for palladium with nickel or cobalt, which is more benign. And of course, it's cost effective and more sustainable. And of course, as you said, you save more money, basically.
Yeah, and you're talking about all these metals that are usually used in the reactions as a catalyst. And catalysis is also that many years back has been not used that much. And since the discovery of the catalyst, that it really helps to reduce the energy needed for the reaction. I think nowadays it's more than 80% of the reactions are catalytic, and we can really have a big impact with the right catalyst. And that's also what your research is about, right? That you are doing catalysis research.
Yeah, so catalysis, of course, plays a pretty important and vital role nowadays. Let's say, for example, if those reactions which we were doing, I don't know, 50 years back by stoichiometric method, where you used to produce a lot of waste and so on. But by using catalysis, now you can basically save a lot of hazardous material and basically make the same process more benign. And I have been involved during my PhD back in LICAT. So I have been mostly involved in hydrogenation chemistry, where, as you probably know, that hydrogenation is very commonly used reductant, or the best reductant so far to me, and which is like well practiced in the industry as well. And I was more involved in the asymmetric hydrogenation, where we were trying to develop new ligands which could be more effective or more selective. So here also we come back to the same point about sustainability again.
Yeah. Maybe for people who don't know what the asymmetric reaction is, maybe let's explain that shortly.
Sure. Yeah. As I was saying, so I had been involved during my PhD doing asymmetric catalysis. So which means we were trying to make one enantiomer of a particular molecule, which is basically beneficial for pharmaceutical application. And asymmetric catalysis plays an important role to make one particular center, where basically you have 4 different atoms attached to one carbon atom. And in principle, we can prepare this basically both the molecules in a same method where they are mirror image to each other. And one of these form of these 2 molecules is basically active in pharmaceutical. So asymmetric catalysis is aimed for making one particular enantiomer of the molecule suppressing the other, which is, let's say, the bad one. And we always aim to make the good one. And so I have been involved in such chemical transformation, let's say.
I think for this, you have one molecule with these chiral centers. That means that this is a connection point where 4 chains or 4 rests come together, and they can be connected in a way that they're a mirror image of each other. And that makes then the whole molecule chiral. And especially in terms of biological activity, oftentimes, whether it's the left-handed or right-handed side, they can have completely different effects. And I think the most famous one is this really tragic example where this thalidomide.
Yes.
It was used to help women in pregnancy with their morning sickness, and later on they discovered that one of the enantiomers would help exactly do that, and the other one would lead to birth defects. And this was really a problem because they figured that out way too late, and then they had this racemic mixture, which means that there's equal amounts of both mirror images present, and then there were a lot of birth defects caused by this thalidomide.
Yes, you nicely pointed out, and people always consider the thalidomide tragedy is basically the basis of asymmetric catalysis, and from then people started putting their efforts in research, like how to make one particular molecule, or whether left-handed or right-handed, in selective manner.
So in your example, what you said, you looked at asymmetric hydrogenation. And what is an example there?
Yeah, so basically, asymmetric hydrogenation, as I already mentioned, has been implemented industrially as well. And since 1980s, Professor Naori and Senors, when they discovered the first asymmetric hydrogenation of L-DOPA precursor back in 1980s, and Naori has discovered the ruthenium binder catalyst for making chiral secondary alcohol. So that's how the asymmetric hydrogenation research started from 1980s or so. And then they also received the Nobel Prize for that. And asymmetric hydrogenation is basically well adapted since more than 40 years, both in academia and industrial research as well.
And then the goal is basically to improve the selectivity towards one of the mirror images. And how does the catalyst help increasing this selectivity?
Yeah, so it depends on a lot of factors, right? So it starts probably with ligand designing. So we need something to stabilize our catalyst, or to be precise, the metal complex or the metal that we use. So that's why we add ligand and to the metal to make the complex, and that basically catalyze the desired reaction in this case. So there is always a thirst or demand to improve the selectivity, whether it's the regioselectivity or a chemoselectivity or enantioselectivity in terms of catalyst design. I was involved particularly during my PhD to make new ligand or to make new chiral ligands, to be precise, for asymmetric hydrogenation chemistry, where at the end, so after 3 years, 3.5 years, I also found that the ligand library that we made also can be applied for a particular pharma molecule, which I worked on. This was a molecule called rasagiline, which is being used for anti-Parkinson therapy. And we could also show that that our ligand basically outperformed the benchmark ligands available or benchmark process available at the time in the market.
Okay, that's great. Especially when it comes to the synthesis of these biologically active molecules, it's not only that you need to have the chiral center ready, but oftentimes they have more than one chiral center, and then they are very complex molecules with a lot of different steps you have to do in the synthesis. And then the homogeneous catalysis plays out its advantages, because usually it's more difficult and more expensive to use the homogeneous catalysts, but in terms of selectivity they can really outperform the heterogeneous ones. And as you said, the ligands really play a role with this. So how exactly do the ligands improve the reactions in that way? So you said already they stabilize the metal center. In what other ways do they influence the reaction?
So first of all, I mean, as you rightly pointed out, the ligand plays really important role in homogeneous catalysis, right? It depends on the reaction. First of all, I could share my story in terms of hydrogenation chemistry, whether hydrogenation of carbon-carbon bonds or carbon-oxygen bond or carbon-nitrogen bond to make optically pure or enantiomerically pure compound. So it influences in different ways. There is a term in chemistry is called bite angle of the ligand. So it's basically define the cone angle bit of the ligand to the metal center. So that also sometimes enhance the fundamental state of our catalysis. So let's say if we have a larger bite angle ligand, that could enhance the fundamental state of a particular homogeneous process. At the same time, if we have a smaller bite angle ligand, that could also enhance the reactivity. And and sometimes solvent also plays an important role, which is often overlooked in academia because, one might have a ligand that, let's say, basically can be degraded in a solvent, particularly solvent, and there one should not expect the reactivity as well. So there are a lot of factors basically, involved or need to be considered for a particular process.
In the best way, you then have your chiral ligand that brings all the selectivity to the one mirror image you want to receive, and then the rest of the catalytic complex also performs the reaction that you want to do, in this case the hydrogenation reaction. And in the past, usually the metal centers for these catalysts were like rhodium or iridium. They are really perfect for catalysis because of their really large orbitals, and they're really flexible, and they can change their oxidation state easily, and that makes them perfect for these catalytic reactions where they interact with a lot of molecules. And what you also did was trying to replace these really expensive rhodium, iridium catalysts with other metals. What's the challenge when you want to do that?
Yeah, as you rightly pointed out, so again, we are also coming back to the same circle of sustainability, right? So in earlier days, we had rhodium, iridium, palladium chemistry. Those has been even practiced at industrial scale for making, let's say, homogeneous catalysis, mainly focus on fine molecule or small molecule pharma, right? Whereas if nowadays, let's say, in last 10 years or 20 years, there has been an increasing concern about sustainability, and also we are trying to replace those metals because, first of all, those are expensive, and those are also toxic. So we don't want to get those metal at our end product.
Yeah, especially for pharma.
Especially for pharma,
Yeah.
right? We don't want to get poisoned by rhodium or palladium or so. And it's pretty hard to remove as well. There might be always some ppm or ppb level of this precious metal left. So now the chemistry fraternity, they're also trying to replace those metals by more abundant or less toxic. I should not say totally benign, like non-toxic, because they also have their toxicity level, but which are way lower than this palladium or rhodium chemistry. And fortunately, I also contributed in this area of chemistry during my PhD, where we were also focusing on asymmetric hydrogenation reaction using a cobalt catalyst. And we managed to get decent selectivity in terms of making one molecule selectively, chiral molecule, let's say, but we also faced several challenges. When we try to move from rhodium or
What was used before you could figure out the way to use cobalt for this reaction?
So people have used rhodium or iridium best catalyst for those reactions, and those were like extremely selective, and those reaction condition could also tolerate decent or super nice functional group present to your molecule, because very often asymmetric hydrogenation is performed at the late stage of the pharma molecule, where you have a lot of functionalities already included in your molecule, and you don't want to rupture those, right?
Yeah.
So in
then
that,
selectivity is even more important when you already have your 5-step synthesis and then you lose half of your product because the selectivity is bad, then it really makes a huge difference compared from what you start and what you end up with, because it compounds from each step, right?
True. I totally agree with you. To me, we are still in the beginning of that journey, because as you probably know, or as we all probably know, that rhodium and palladium chemistry or precious metal chemistry is basically has mixed with our blood. So it's pretty hard to, get rid of those chemical processes, even for the industry, because if they have to change a method for a particular synthesis, let's say for a pharma molecule or so they need to change the whole engineering, the whole setup for a particular molecule, which is of course time consuming, which need more research and more collaboration with industry together with the academia. Yeah.
But there they usually have one reaction and then they scale it up. They do it in the pilot plant and then they go to the big plant, but they basically have this one reaction and they do everything to get every percent out of it. Whereas from the academic point of view, the problem is a bit different, right? You mentioned in our discussion before that it's really important to show that your catalyst can do many reactions.
Yeah.
Where does this difference come from the industry to academia?
Yeah, I think there's a never ending discussion why there is always conflict between academia and industry. But I try to take it in a positive way because in academia, let's say I try to develop a method for a particular transformation, and we try to generalize the method as much as we can, right? We also sometimes in academia try to make some pharmaceutically active molecule, whereas in industry they are particularly focused on one molecule, right? So let's say, yeah, I mean it depends on the particular project, but I still think that the collaboration between the industry and the academia would definitely faster this transition, let's say, from the existing condition to the more benign condition. So let's say more sustainable process, right? So I think this will definitely, be the key factor for our way to go. So
Yeah. Do you think there is an difference whether the research is funded by industry or funded by the public when it comes to these kind of goals?
I still think, like to my knowledge, the industrial funded program are really limited, as you rightly pointed out, that they're really focused, right? So they're really limited, and to me, what I experienced or what I learned is they also approach to selective people. So, but they are also open for discussion or open for collaboration. Whereas for the publicly funded projects, you have some more money, more freedom, and more possibility, right? So I still believe that where you have more money, more freedom, and more possibility, you invent more or you discover more, more open mind. Whereas in industrial project, because I also worked on an industrial project back in LeCat for 6 months. So you had sort of time pressure, so you need to deliver the result because they have time pressure for the next day, right? So it's all connected.
Yeah.
So we also cannot blame them or argue with them because it's all are connected. So we need to deliver our stuff. So I mean it depends. So
Yeah,
yeah.
I think it's also with this, when you have this fundamental research where it's partly really out of curiosity of the researcher that you do something and then you get a result that you didn't expect, and then you think about why did this happen now, and then you want to figure that out, and then this goes from one to another, and then you basically find out a new reaction that can outperform the benchmarks. And then you also want to, okay, we have this new catalyst, what else can it do?
Exactly.
Whereas in industry, that's like flipped. You have a goal, one reaction, which is a bit more limited. When you have the freedom to do the research, you can also go after different problems that you didn't even know existed before.
Yeah, I totally agree with you. But we should also think from their perspective as well, because they have their own timelines and own constraint, right? So at the same time, but I think now people are more open. So even let's say they have a process, they want to change the process for medchem or discovery chemistry, they do allow R&D, research and development, for a year or two or so for a particular process before going to, like implementing it on scale or so. So I think they are more open. That's what I said. So we should have this sort of synergy between the academia and industry, so that we both of us get benefited, and at the end we are serving the societies to the community, right?
Yeah, that's also especially in America at the moment, where they're really cutting the funding for a lot of the fundamental research, and they only want to do like the applied research. But in the end, you need both.
I totally agree with you. And I would say that most of the great discovery so far came out of fundamental research. And so,
Yeah.
So we need fundamental research, of course. I was lucky, in fact, I was also involved in fundamental research in Rostock and here in Mulheim as well. And by this, I'm also learning like how to implement the fundamental chemistry to the broad horizon, So yeah, I totally agree with you. So fundamental chemistry should come first, and then basically based on the study or based on the case what we want, then we go for the applied research. And there also we need collaboration, because we, coming from an academic background, we might not have that expertise that chemical engineer has, right? So
Yeah, definitely.
Yeah, so I truly believe that we should definitely have this synergy to go forward. Yeah.
Yeah, that also reminds me a bit of my research in Dortmund, where we were engineers and chemists together. And sometimes in our weekly discussions, when the chemists were talking about their results, and then the engineers were like, yeah, but that will never work like this in the industry. When you scale this up and then you think about the costs, and then we had to also, a bit earlier than others, I would say, think about, for example, how to retrieve your catalyst from the reaction mixture. That was one of our key topics there, to separate these homogeneous catalysts, which is a big disadvantage of them, and have these concepts in mind early makes it then also easier later to implement this new reaction than in a bigger scale. But yeah, we still need the new catalysts and explore what's possible there.
True, I totally agree.
What do you think the catalysis research will look like in the future? When we think about all these developments in AI and such, do you think they will also have an influence on this catalysis research?
Yeah, there's a tough point to be this. I mean, nobody can predict future except AI now.
Yeah.
But I truly believe that sustainable chemistry, of course, should be at the first place, right? As I was mentioning, even if you improve the reaction temperature, or even if you improve the catalyst loading, let's say from 10 mol% to 0.1 mol%, or even if you improve the selectivity of the reaction, that also becomes sustainable. So I would still put sustainable research at the first place. As you rightly mentioned, the AI, of course, it's getting hype nowadays. Of course, this could improve our, let's say, daily methodology that we use very often. But before AI, I would even more emphasis on data-driven approaches, right?
Yeah.
Because we have billions of data, and we don't know how many of them are really correct, So we really have to, or people should really have to focus on making correct or actual data set, those are working data set, let's say, and by that we can definitely learn, let's say for a particular transformation, which metal we need to choose, or with which kind of ligand we need to choose. So data science is really important.
Another collaboration, right?
And
Not only chemists and engineers, but also nowadays chemists and data scientists.
Data scientists, yeah, I totally agree. Another point I would like to highlight is high-throughput screening, which is basically, let's say, we as a chemist, whether PhD or postdoc or a technician in a lab, let's say if they can run 10 reactions a day, which is super ambitious, by the way, whereas one could use the machines or robots to do that. If, of course, the process has to be robust, and yeah, I mean, in most of the cases, we choose those reactions which are relatively simpler, right? So so as I was saying, so a machine can do, let's say, 96 reactions in a day, and that could definitely fasten the process of screening or for a methodology development or so. So yeah, sustainable chemistry, data science, of course, and high throughput screening as well. And of course, now with the incorporation of machine learning and AI, I mean, if one has to focus on a particular process or particular method development, then definitely one has to incorporate all four of these points, and then he or she will definitely get a better result than the trivial or classical way. Yeah.
Are you already using this high throughput screening in your work?
I have used it once. I had the opportunity to visit to University of Amsterdam during my PhD time for an exchange student, and there they had a machine they used to call RoboChem, where they basically could run 96 reactions. Like I was doing hydrogenation chemistry, 96 reactions. So they literally had 96 in small autoclaves. So autoclave is basically a pressure vessel where we run the high pressure reactions, and one can literally tune each and every parameter for each autoclave. So you could imagine that you could literally run 96 reactions with 96 different, minimum 96 different parameters.
Yeah.
So yeah, I had the opportunity to use it once, and that basically within 3 days, I got my optimized catalyst.
Yeah, that's then also a huge time saving, right?
True.
When you think about the classic organic synthesis where you do like your 3-gram reaction and then you do all the workup and then you have to refine the product, and in the end you have a yield by just weighing your
material
product.
Yeah.
That's very slow compared when you have a robot that can basically do the reactions, and they probably also use GC or
exactly
stuff like that to figure out what the reaction outcome is without this really complicated workup procedure.
Exactly. So as I said, for a small molecule pharma, so for a particular process, so for really focused project, this really helps if you know what to do. And usually it helps a lot, and like it saves time, right? Which is proportional to the money, right?
Yeah.
And which gives you indirectly more time to invest on different things or different projects. So yeah, I totally agree with you. Yeah.
Yeah, that's a really good method of creating the data, and then now that still has to be improved. Really make sure that the data is high quality, and with high quality data then you can use all these AI models or data driven approaches, but when you don't have good data they also don't bring you anywhere. So
true. Yeah.
Nice. Okay, then as the last question for this discussion, I asked the people what's their favorite discovery in chemistry. So what's yours?
Oh, let's be honest. I probably love most of the chemical reaction that I have been involved from my master's till now. But in terms of favorite discovery, let's say, okay, now I'm being more political. So during my PhD, so basically we also made a library of chiral ligand that I was discussing with you that also outperform certain reactions on the benchmark ligand. And we also named the ligand. So it's basically a bidentate phosphine ligand. We also named the ligand Josephus. So Geophos Johannes, which is my PhD supervisor. So for Soumyadeep. So I could
Oh,
proudly
that's nice.
say that, yeah. So we tried, let's say, to make a new library of ligand. Yeah. Tried benchmark reaction to see the activity, because you always have to see whether your ligand is active for benchmark reaction and so on. And then you applied your ligand to a real-time pharma. That also I was fortunate to achieve during my PhD. So I would say, yeah, the Josephus is the best.
Nice. Yeah, that's really cool to have your name on a ligand or on a reaction. When you're in your bachelor's, you learn all these name reactions, and then this, and now you can call one of the ligands
Yes.
yours. Yeah, that's really impressive.
Yeah.
Okay, yeah. Thank you for this nice discussion. Thank you for your time.
Thank you very much, Kevin, for the invitation as well. I really enjoyed.
Also, thank you very much for listening. Don't forget to follow on whatever app you're using. If you want to be part of a future episode, contact me via email through contact@innovateandreact.com or find me on LinkedIn. Until next time, keep innovating and stay curious.